Hello viewers, in today's class we are going to discuss yet another important application of Lagrange's mean value theorem, right? So here in this lecture we are going to discuss the condition for a function to be a decreasing function with the help of Lagrange's mean value theorem, right? Or in other words, we can say that here we'll prove the condition for a function to be a decreasing function in some interval using Lagrange's mean value theorem, right? So here we have the statement that using the Lagrange's mean value theorem, show that if f of x is continuous on some interval a comma b and f prime of x is less than 0, that is the derivative is less than 0 in some interval open interval a comma b, then f of x is a decreasing function in the interval a comma b, right? So let us start. So here we can take the axis. So here we have the axis, this is x-axis, and here we have the y-axis, and this is the origin, right? So now let us take the function, say y is equal to f of x, and let us take the function like this, right? So this is a decreasing function, and let us take this point as a and this point as b, right? And here we'll take the point x1, and here we'll take the point x2, right? So from a to b, this function y is equal to fx is a decreasing function, right? So now we know that here x2 is greater than x1 because this number x2 is greater than x1, but f of x2 is less than f of x1, right? So this is the condition for the function y is equal to f of x to be a decreasing function, right? So here this is f of x1 and this is f of x2, right? So if y is equal to f of x is defined on some domain, and x1 and x2 belongs to that domain, and if x2 is greater than x1 but f of x2 is less than f of x1, then we can say that this function y is equal to f of x is a strictly decreasing function, right? So here our aim is to derive this condition with the help of Lagrange's mean value theorem, right? So let us start, and let us first see whether the condition of Lagrange's mean value theorem are satisfied or not. Although the conditions of Lagrange's mean value theorem are already given in the statement, right? So now here we have the function y is equal to f of x, right? And this function is defined in the interval a comma b, right? And let us take 2 points x1 and x2 belonging to this interval a comma b, such that we form an interval, say x1 comma x2, right? And here x2 is greater than x1, right? Okay, now the first condition of Lagrange's mean value theorem is that this function y is equal to f of x should be a continuous function in the interval x1 comma x2, right? So here this interval x1 comma x2 is a subset of this interval that is a comma b, right? So here we are already given that f of x is continuous on a comma b, and x1 x2 belongs to this interval a comma b, or in other words we can say that x1 x2 are two distinct points in the interval a comma b, right? So f of x is obviously a continuous function in the interval x1 comma x2, right? And the second condition is that f of x is differentiable, right? So here we are given that the derivative of f of x, it exists and it is less than 0 in a comma b, right? So f of x is differentiable in the open interval x1 comma x2, right? So here the conditions of Lagrange's mean value theorem are satisfied. So Lagrange's mean value theorem says that once the function is continuous function and differentiable function in the given interval, then there must exist some point c where c lies between x1 and x2, right? And this point c, which lies between x1 and x2, is such that f prime of c must be equal to f of x2 minus f of x1 divided by x2 minus x1, right? So this is the condition for Lagrange's mean value theorem, right? Okay, so now what we will do further, we'll utilize this statement to arrive at this condition, right? So see here, f prime of x is less than 0 for the interval a comma b. So we are given that f prime of x is less than 0 in a comma b. So obviously f prime of x must be less than 0 in the interval x1 comma x2, right? Because x1 and x2 are two distinct points in the interval a comma b, right? So here c lies between x1 and x2, right? So c lies between x1 and x2. So obviously this derivative at this point f prime of c must be less than 0, right? So now here f prime of c is less than 0, and here we are given that x2 is greater than x1, right? So x2 is greater than x1, it implies that x2 minus x1 is greater than 0, right? So now here f prime of c is less than 0. It implies that f prime of c is a negative quantity, right? So f prime of c is less than 0 implies that f prime of c is a negative quantity and x2 minus x1 is greater than 0. So this implies that x2 minus x1 is a positive quantity, right? So from this expression, if we take x2 minus x1 to this side, that is if we multiply these two quantities, then we have f prime of c times x2 minus x1 is equal to f of x2 minus f of x1, right? And now see, f prime of c is negative, so here we have negative, and x2 minus x1 is positive, so here we have positive quantity, right? So this is equal to f of x2 minus f of x1, right? So here we are interested in the sign of f prime of c and x2 minus x1. So here we have negative uh, sign and here we have the positive sign. So negative times positive is negative, right? So we have fx2 minus f of x1 is equal to a negative number. So it implies that this difference is less than 0, right? So it means f of x2 minus f of x1 must be a negative quantity, that is less than 0. So we have f of x2 is less than f of x1, right? And which is this condition, that is f of x2 is less than f of x1 for x2 greater than x1. So here we have x2 greater than x1, right? So this is how we can prove that a function f of y is equal to f of x is a strictly decreasing function with the help of Lagrange's mean value theorem.